What we're going to be exploring is chord properties. So chords are those line segments that connect from one side of a circle to another. And we're going to explore some new and old vocabulary. So please take out your notes from the circle vocabulary that we introduced 2 classes ago. And we're going to add to those notes. We are going to explore some cool properties, and we're going to do some practice problems throughout. So the first term I have is an old vocabulary term, which is called the central angle. So go back to your notes and tell me which of these definitions is the correct definition of a central angle. So the correct definition for a central angle is an angle whose vertex is the center of the circle and whose sides pass through the endpoints of an arc. So if we're looking at this blue central angle, its center of the circle is the vertex, and A and B are both the endpoints of an arc. So these together from the center to the endpoints of the arc create that central angle. Now we go on to arc measure. This is also an old term. So tell me, based on the picture and based on your old definition that you already have, what is the definition for arc measure? So the definition for arc measure is the measure of the central angle that intercepts an arc, measured in degrees. So this measurement of 47 degrees is how we measure arcs. They're measured in degrees, similar to how angles are measured in degrees. And they actually are exactly the same as the central angles. So if we look at this 85-degree pink arc, this central angle O is also 85 degrees. Now, quick question, should be an easy one. How many degrees are in a circle? Good. It is 360 degrees are in a circle. It's always good to make sure we remember which shapes have how many degrees. A circle is 360 degrees. Now we're moving into some new vocabulary, so have your pencils out to add to your vocab sheet. The first term I have here is called an inscribed arc. Sorry, my bad. An inscribed angle. And you'll see that this blue angle represents an inscribed angle, this purple angle represents an inscribed angle, and this pink angle represents an inscribed angle. What I want you to do is look at the picture and look at the definition options and tell me which of these options you think is correct. So the correct definition for an inscribed angle is this first one here, an angle whose vertex lies on a circle and whose sides are chords of the circle. So, meaning if we're looking at this blue angle right here, an angle whose vertex lies on the circle, so you can see point B lies on the circle, and whose sides are chords of the circle. So side AB is a chord, side BC is a chord, making angle B an inscribed angle. So what I want you to do is write down this definition and include a sketch of the different inscribed angles. The next term I have for you guys is called an intercepted arc. And looking at the picture and the definition options, tell me what you think the definition of an intercepted arc is. So an intercepted arc is an arc that lies on the interior of an angle with endpoints on the sides of an angle. So this just points out that continued observation that this interior angle, this central angle and this intercepted arc right here are going to be congruent. Add that term to your vocab list. So intercepted arc, include the image, especially with the labels of the 40 degrees to point out that the central angle and the measure of an intercepted arc are congruent. So now we are going to move on to the more interactive portion of this lesson. If you want to try to follow along with how I'm doing this, you can go to the link of the activity and mess around with the ability to move the different portions of the line to see things a little bit more clearly for yourself. I'll try to do the best I can, but know that you can go to this link and also play around with the circle yourself. So what we have here is a circle and two chords, chord DE and chord CB that are congruent. Those tick marks are indicating that these sides are going to be congruent. So no matter how much I move them, you'll see that the chords still have those tick marks, making them congruent. What else do you notice is happening in this situation? As I change the size of the chords as they say congruent, what do you notice about the central angle measurements that are listed right here? And I'll play around with it a little more as I change the length. If I make the circle smaller or bigger. So now we're going to move into this first chord central angles conjecture, which is going to get added to your notes. The chord central angle conjecture states if two chords in a circle are congruent, like how CB and DE were congruent, then they determine two central angles that are what? Congruent, supplementary, or complementary. What is going on with those? If two chords in a circle are congruent, then they determine two central angles that are congruent would be the answer we're looking for. So that's what we're going to write down in our conjectures with our circle notes. It's called the chord central angles conjecture, and it states if two chords in a circle are congruent, then they determine two central angles that are congruent. All right, let's move on to the next one. So that same figure is going on here. So if we have two chords that are congruent, then based on the fact that we know their central angles are congruent, what can we also say is congruent? Which of these terms, we already know their central angles are congruent, so we're not going to say that. If two chords in the circle are congruent, then their what are congruent? Then their intercepted arcs are going to be congruent. Yes, their central angles will still be congruent, but we already proved that. So this is going to be going one step further. So the intercepted arcs are also going to be congruent, because whatever the angle of the central angle is, the arc measurement is going to be the same. So if measurement of BAC, this central angle right here, is 68.67, we also know the measurement of arc CB is 68.67 as well. All right, moving on. These are going to be some example problems. So we have hexago is a regular hexagon inscribed in a circle. Inscribed just means it's set within a circle where each vertex is lying on the edge, making each of the sides of the hexagon a chord. So line segment HO is a chord, OG is a chord, GA is a chord, and so on. And since it's a regular hexagon, each chord is congruent to one another. So based on that, and knowing that a circle has 360 degrees, right, what is the arc measure of arc OH? So the arc measure is going to be 60 degrees. And the reason why is because if each of these arcs are congruent, because each of these chords are congruent, and there's 360 degrees total in a circle, and that's split up evenly among the 6 chords, then we can do 360 divided by 6, which leaves us with 60 degrees. All right, one more problem kind of similar. What we see here is a chord MQ that is congruent to a chord QT. We see that this arc is 150 degrees. What do you think the measurement of angle P is? So let me help you through this process a little bit. So if we know that TQ is 150 degrees, arc TQ is 150 degrees, and we know that chord TQ is congruent to chord QM, we also know that this arc is congruent as well, making arc QM 150 degrees. So you're going to add 150 plus 150, which is 300 degrees, and then you'll be able to find the rest of this arc MT, which is going to be 60 degrees. And then whatever the arc's measurement is congruent to the central angle of angle P. So our answer is going to be 60 degrees. We have one more kind of straightforward question. Looking at this circle here, we know that this central angle is going to be 70 degrees, and this chord is creating that central angle. It's going from the two endpoints of the arc. If this chord is congruent to that chord, what is the measurement of W? The measurement of W is going to be 70 degrees, because if the chords are congruent, their central angles are also congruent. All right, now we're going to move on to the second exploration. What we have here is once again two congruent chords. So chord DE is congruent to chord BC. And we have a perpendicular going from point A to chord BC and a perpendicular line going from the center of the circle A to chord DE. The reason why we would create a perpendicular is to find the distance from the center of the circle to that chord. But what I want you to first notice is no matter how much I change the full length of the chord, this perpendicular line does what to the chord? If you look specifically here, so BF, this portion of the chord is 2.81 and CF is 2.81. Similarly over here, DG is 2.81 and GE is 2.81. And notice as you change it what is also happening throughout that time. So think about that and let's try to fill in the rest of this conjecture. The perpendicular to a chord conjecture. We have this purple line is a perpendicular to a chord. The perpendicular from a center of a circle to a chord is the blank of the chord. Is it the end point of the chord? Is it the bisector of the chord? Or is it the angle of the chord? It is going to be the bisector of the chord. So if you have a perpendicular line going from the center of the circle to a chord, then that is automatically going to be bisecting that chord into two congruent pieces. That's going to be something we now add to our notes, the perpendicular to a chord conjecture. The perpendicular to a chord conjecture says that the perpendicular from the center of a circle to a chord is the bisector of that chord. One more exploration involving the same image here, right? So we still have that same image. We figured out that the chord is getting bisected, but now what I want us to look at is the actual perpendicular bisector itself. So that perpendicular line going from the center to the chord is helping us calculate the shortest distance from the center to the chord, from the center to the chord. And we're also going to keep in mind that chord DE is congruent to chord CB. So let's try to fill in the chord distance to center conjecture. Two congruent chords in a circle, like we have here, are blank from the center of the circle. Are they equidistant from the center of the circle, different distances from the center of the circle, or equiangular? And let me just move this around to show you a couple examples, if that helps. Do you think two congruent chords in a circle are equidistant, different distances, or equiangular from the center of the circle? The answer is going to be equidistant. Whoops. This distance of line segment AF is congruent to the distance of line segment AG, no matter how much we move or change this circle. All right. So now that we're going to add that to our notes, this is going to be the last addition to our notes before we just do some practice problems to end class today. We have 6 more problems for class, and then we can wrap it up. So this first one I have here is question 4 here. It says that AB is equal to CD, meaning that this full chord is congruent to this full chord. We know that line segment PO, this perpendicular from the center, is 8 centimeters. And what we want to figure out is how long is OQ. So do you think it's 6 centimeters, 8 centimeters, or 9 centimeters? It is going to be 8 centimeters because the perpendicular to congruent chords are always the same distance. So since we knew that the chords were congruent from that first statement, and we knew the distance of PO, we knew that the distance from OQ would also be the same. So that's also going to be 8 centimeters. Let's move on to the next question. It says, what is the value of Z? So we see that this arc is 128 degrees with a chord that is congruent to this chord. We also see this little tiny chord over there is 20 degrees. We want to figure out how many degrees is Z. So the answer is 84 degrees. If we first determine, since these chords are congruent, we know that this is 128 degrees. We also know the other arc is going to be 128 degrees as well. So we would do 128 degrees plus 20 degrees plus 128 degrees, find what that is, and then subtract that value from 360 degrees to find the measurement of Z. Now we see this problem that says, what is the value of W? So looking at this picture, W is right here. It's asking what is the measurement of arc W? Arc W is going to be 115 degrees because the arc is always the same as the internal angle. Very similar question, same picture. Now we're looking for the arc X. How many degrees is the measurement of arc X? Arc X is also 115 degrees because we have this chord AN, which is congruent to chord GN, making arc W having to be congruent to the measurement of X. So they're both going to be 115 degrees. Moving on to another one like this, very similar. We are now looking for the value of Y, and Y is right here, where we are going to try to figure out what is the measurement of it. So try that out. All right, so the answer is 65 degrees. And the way you do that is you know that W is 115, X is 115, so you would add those two numbers together, and then you would subtract them from 360 to figure out how much is missing for arc AG. Once you find that value, which is 130, you're going to take that number and divide it by 2 because we can see that these are going to be congruent. They're also going to be just half of the value. So Y is going to be half of 130, making it 65 degrees. We're going to skip over this question because it actually is the wrong picture. I put the wrong picture in, and we're going to skip just to this last problem where it says, what are the values of W, X, Y, and Z? So what I want you to do is type in your answer. Just say W equals blank, X equals blank, Y equals blank, and Z equals blank. Oh, and noting that this is important, arc AC is 130 degrees. If you missed that piece of information, this would be very difficult. So W is going to be 110 degrees. X is 48 degrees. Y is 82 degrees. Whoops. And Z is 120 degrees. I'll walk you through how to do that really quickly. So W, which we see right here, is the arc, which is going to be congruent to its central angle. So W is also going to be 110 degrees. X is going to be the opposite, where the central angle is 40 degrees, so the central angle will also be 48 degrees. Since we knew that arc AC was 130 degrees, to find Y, since A to C is going to be 130, and this portion BC is already 48, we can find that the arc AB is going to be 130 minus 48, giving us 82 degrees. And then to find arc that's being represented by Z, we're going to add up 48 plus 82 plus 110 to find our missing value of Z, which is 120 degrees. All right, guys, that's all we have today. I know this was kind of a longer lesson. If you have any questions, please feel free to reach out, but this is all we have for today. So I hope you have a great rest of your day, and I'll see you next class.